Okay, so in this example we're told that block B has a constant acceleration to the right, and at the instant shown block B also has a velocity to the right. And given this information, we're asked to determine the velocity of block A, as well as the acceleration of block A. Now in problems such as this, what we're going to utilize is something known as the rope length constraint. The basic idea here is that the cable or rope connecting, in this case blocks A and B, is of constant length, and thus we can use that fact to get information about the relative speeds or relative velocities as well as relative accelerations of the block. And the way I'm going to do this is I'm going to start by defining a position or a coordinate in the system, if you would, where there's essentially a datum. I'm going to choose to use this fixed stop on the ground as my reference point. What I can then do is I can say that block A is going to be located some distance that I'm going to choose to call SA away from that point. And also I can use somewhat similar logic to say that SB will be some distance away from that datum as well. Now what's the benefit of this? Well, what I can do is essentially add up different rope length segments now. And so if I do that, I'll note that this segment here, as well as this segment here and this segment here, are all of length SB. So I'm going to have, in this case, 3 times SB as part of my ropes. And then if I look on the other side using somewhat similar logic, I have 1, 2, 3, 4 rope length segments of length SA. And so my rope length constraint equation is going to tell me that 3SB plus 4SA has to equal some constant, with that constant being the total length of the rope. Now once I have this piece of information, I can take successive time derivatives to get relationships between the speed of block A and B, as well as the acceleration. So let's go ahead and start by taking the first derivative. If I do that with respect to time, I'll have 3 times the speed of block B plus 4 times the speed of, the speed of block A, which will be VA, will equal 0. If I take a time derivative of that yet again, I'll have that 3 times the magnitude of acceleration of block B plus 4 times the magnitude of acceleration of block A will equal 0. Now let's go ahead and call this equation 1 and equation 2 respectively. If I take the information I get from equation 1, what I'm going to have here is that the speed of block A is going to equal, in this case, minus 3 times VB divided by 4. If I want to make this a vector, I'll note in this case that because SA is actually positive to the left, VA would be positive to the left as well. Thus, when the when the speed turns out to be a negative number, if I want to convert this to a velocity, I need to multiply it by a minus sign, and that's going to give me a number in the I. I think this makes sense to us. It simply says that if block B is moving to the right, as indicated in the problem statement, then A will be moving to the right as well. I can use somewhat similar logic on equation 2 to get a relationship between accelerations. Namely, I can say that the acceleration of block A is going to be, in this case, minus 3AB divided by 4. And if I take that scalar and again convert it to a vector, noting that again SA is positive to the left, then I'm going to get the acceleration of block A is going to be 3AB over 4 in the I direction. Okay, at this juncture all one would have to do is plug in the numerical values for the two quantities given, and you'll be good to go. I'll leave that up to you to do. Best of luck.